We started reviewing technical papers on platinum production, and the first one we looked at was a paper published by Dr. Ulrich Klotz and the FEM team back in 2019. It is a very impressive and informative paper with a lot of critical points on platinum investment casting. So, following our previous discussion, and to answer the question whether we should be casting our platinum with superheat, we're going to go a little deeper into this discussion to find out how superheat could be a solution for some of the casting defects, but at the same time, how casting at too high of a temperature could yield to possible casting defects. The most common concern when we're casting platinum, especially with alloys like platinum ruthenium, it's form filling. Platinum ruthenium is probably one of the more challenging alloys when it comes to form filling just because of its limitation in its fluidity. It just doesn't flow very well. One of the analogy we use is platinum ruthenium flows like porridge as opposed to milk. Platinum ruthenium also has a higher temperature, which means you have to keep it very hot, to keep it in its liquid state, to keep it flowing so it doesn't solidify before it reaches its destination. Superheat is casting above the melting temperature. That's going to give the liquid metal more thermal energy. And this is going to help by reducing its viscosity, by increasing its fluidity, and make sure it flows quickly through the narrow channels and into the intricate mold cavities before the metal solidifies. Oh, another great analogy I read. Cold honey is hard and difficult to pour. Warm honey, on the other hand, is thin and flows into every corner of your spoon. We definitely want our platinum to cast like honey. Two common casting defects that often occur with insufficient superheat are misruns and cold shuts. Misrun is when the metal solidifies too quickly before it fills the entire mold, resulting in no fill and incomplete parts. Cold shut is when two streams of molten metal meet inside the mold, but have cooled so much that they don't fuse together properly, leaving a line in the casting. How superheat helps is by providing a time buffer to make sure the metal is hot enough, it's liquid enough, and it's fluid enough to fill the entire mold, and for separate streams to come together and merge seamlessly. And this time buffer is especially important for platinum because its melting temperature is significantly higher than the flash temperature, which means heat is lost the moment the metal leaves the crucible and into the cooler environment. The superheat helps to counter the heat loss, acting as a thermal reserve to make sure the metal is hot enough that it will flow and fill even when heat is lost along the way. Figure 7 in Dr. Ulrich's paper illustrates how heat is retained when we're casting at a superheat of 1980 Celsius. He has authored numerous papers on casting simulations based on computational fluid dynamics. Now, I believe this whole concept would be better explained if we can show animations of casting simulations, and hopefully this is a topic that we can cover very soon on our channel. And speaking of which, please subscribe and like because we're working very hard to bring you weekly content on platinumABC. Two other reasons why superheat could help with a better casting, but I would really only consider these points along with other factors that could potentially have more drastic impact on my castings. The first is extra heat and time. That's going to allow gases to move to the surface and escape, so that could decrease the chance of gas porosity. Though superheat helps with this, it's not a number one concern because if you're experiencing too much gas porosity in your casting, maybe we're already going too hot. The second reason is melting at higher temperature, but when cooled properly, could result in finer grain structure. So when metal solidifies, they form grain structures. Large columnar grain structures is going to yield a weak metal. On the other hand, a fine, aqueoxed, and uniform grain structure is going to give you better mechanical properties like a higher tensile, higher toughness, and higher yield strengths. Again, while superheat can help, it is not the only factor that's going to have an influence on the fineness of grain structures, because as you know, every little detail is going to count when it comes to casting. But like we said in the last episode, too much heat can also be a problem and cause defects. I've taken these quotes out from the paper. You can pause it and read it for yourself. Adding more heat adds more stress into the system, and as a result, more defects can arise. As the quote suggested, metal molten reaction could lead to a rough casting surface. Higher temperature could sometimes lead to greater thermal contraction, and as the metal cools, lead into shrinkage porosity. Higher temperature could potentially erode and wash away the mold walls, resulting in casting deformation. And finally, too higher temperature could potentially create more gas porosity because hotter metal dissolves more gases. So do we superheat when we cast platinum ruthenium? Absolutely. The recommendation is that you go 100 to 150 degrees above the melting temperature of the alloy. And it all depends on the designs of the product and how big of a tree you have. The finer the product, if you have filigree or if you have got a big tree to fill, you can go a little bit higher on the temperature. But remember, just because you're casting at a higher temperature doesn't mean that you're going to get a better casting. Someone once said, superheat is like the Goldilocks principle to casting. Too little, you're going to run into cold shots and misruns. Too much heat, you're going to run into rough surfaces, gas porosity, and possibly mold erosion. So just at the right temperature, when that porridge is just right, you are going to get a better casting.